Hey kids, welcome to section 5.2 Mean, Variance, Standard Deviation, and Expectation. Today, you are going to learn how to find the mean, variance, standard deviation, and expected value for a discrete random variable. So, think back to chapter 3 when we first learned how to find mean. And when we were finding the mean of a sample, we would add up all the values and divide by how many numbers we added up. If we were doing population mean, we would use mu and a capital N. So to put this together with what we're going to talk about now, to find the mean for a probability distribution, you're going to multiply each possible outcome by its corresponding probability and then find the sum of all those products. So here is the official definition right here. Okay, let's make that a little better. The official definition, mu is equal to the sum of all of the x's times the p of x's. So you're going to take each of the outcome values, each of the discrete variables, multiply it by its corresponding probability, and then we're going to add them all up. The rounding rule for the mean, the variance, and the standard deviation is one more decimal place than the outcome x. So if your discrete random variables have no decimals, then your mean, variance, and standard deviation will have one. Okay, so let's take a look. Find the mean of the number of spots that appear when a die is tossed. Okay, well, before we can find the mean, we first need to come up with the probability distribution. So if we create a probability distribution for x and p of x, well, the number of spots that appear when a die is tossed. You've got 1, you've got 2, you've got 3, 4, 5, and 6. Well, each of these appears 1/6 time. So they have a 1/6 probability of showing. So to find the mean, we're going to take each of the x's and multiply them by their corresponding p of x's. Then we're going to add them all up, the sum of all the x times p of x's. So the mean is equal to the x1 times the probability of 1/6 plus the next x2 times its probability of 1/6 plus 3 times a sixth plus 4 times a sixth plus 5 times a sixth plus 6 times a sixth. So we're going to take each of the random variable x's and multiply it by its corresponding probabilities, and then we're going to add them all up. When we do this, we get 21/6, which is 7 halves, which is 3.5 spots. So when we roll a die, the average number of spots that shows is 3.5 spots. Obviously, you can't roll a die and get 3.5, but that is the average. If you were to keep adding the number of spots that you see when you roll a die, the average would be 3.5. All right, the next example, children in a family. In families with 5 children, find the mean number of children who will be girls. Okay, so we're not going to find all the different outcomes. That's crazy. So let me tell you that you can have between 0 and 5 girls. So 1, 2, 0, 1, 2, 3, 4, and 5. Now there are 32 different choices. There's only one way not to get any girls. So 1 over 32. There are 5 out of 32 ways you can get one girl. 10 over 32 to get 2 girls. 10 over 32 to get 3 girls. 5 over 32 to get 4 girls, and one way to get all 5. So if I want to find the mean, I take each of my x's and multiply by their corresponding p of x's, then add them all up. So 0 times 1 over 32 plus 1 times 5 over 32 plus 2 times 10 over 32 plus 3 times 10 over 32 plus 4 times 5 over 32 plus 5 times 1 over 32. All right, so if I do this, I get 80 over 32, which is 5 over 2, which is 2.5 girls. Obviously, you can't get half a girl. There's no torso running around. But so this would be on average if you were to find the number of children who in a family, you would notice that 2.5 girls is the mean amount. Okay. Next example, if 3 coins are tossed, find the mean of the number of heads that occur. Okay, so I need a probability distribution first with our x and p of x. So if I flip a coin 3 times, my probabilities go with the random variables of 0 heads, 1 head, 2 head, and 3 heads. We've seen this distribution a few times. That's 0 heads is 1/8 of the time, 1 head is 3/8, 2 heads is 3/8, and 3 heads is 1/8 again. So if I want to find the mean of the number of heads that occur, I'm going to take my 0 multiplied by 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Okay, if I do this, my mean mu is 12/8, which is 3 halves, which is 1.5 heads. That kind of makes sense. If I flip 3 coins on average, I get 1.5 heads. Obviously, you can't get half a head, but that's an average. Okay, the last example here, the probability distribution shown represents the number of trips of 5 nights or more that American adults take per year. That is, 6% do not take any trips lasting 5 nights or more. 70% take one trip lasting 5 nights or more per year, and etc. Find the mean. So again, you're going to take your mean, you're going to take each of your x's and multiply it by its corresponding p of x's. So 0 times 0.6 plus 1 times 0.70 plus 2 times 0.20 plus 3 times 0.03 plus 4 times 0.01. When I multiply and add these all up, I get 1.23 trips, but I can only have one more decimal than the variable, and so this is 1.2 trips. So on average, families take 1.2 trips that are 5 nights or more. Okay, so that's how you calculate mean. Let's now calculate and talk about standard deviation and variance. So think back to chapter 3. We learned that variance was sigma squared. You took each of the x's, subtracted the mean, squared them, added them all up, and divided by how many numbers there were. And then we knew that the standard deviation was the square root of whatever the variance is. Well, the same can be found using a probability distribution, but we have to use a slightly different formula. So to find the variance for the random variable of a probability distribution, you're going to subtract the theoretical mean of the random variable from each outcome and square the difference, then multiply the difference by its corresponding probability, and then add the products together. I know that sounds crazy, but we'll do it together. So the variance is right here in the box. You're going to take each of the random variable x, square them, multiply them by their corresponding probability, add them all up, and then subtract the mean squared. And then to find the standard deviation, you're going to square root that. One more decimal than the x value that was previously said. So compute the variance and standard deviation for the probability distribution for the number of spots that appear when a die is tossed. Okay, so previously on another slide, we had the distribution 1, 2, 3, 4, 5, and 6, and each of the corresponding probabilities was 1/6. And in a previous slide, we calculated the mean to be 3.5. So we're going to now compute the variance and the standard deviation. So the variance is sigma squared. You're going to start by taking each of the x's and squaring them and multiplying them by their probabilities. So 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6 plus 4 squared times 1/6 plus 5 squared times 1/6 plus 6 squared times 1/6. Then I'm going to close off my parentheses, and the formula says we're going to subtract the mean squared. In this case, the mean is 3.5 squared. So if you type all this into your calculator, trust me, you get 2.9. Okay, then the variance is going to be, oh, and by the way, that 2.9 was rounded because you can only have one more decimal than the x's. So when I try to find the standard deviation, I'm going to square root the variance. Make sure that you square root whatever number is on your calculator. Don't just square root 2.9, but square root all of the decimals because we only want to round as much as as least as many times as possible. So if we square root whatever's on our calculator, you should get 1.7. So what does this mean? This means that on average, we're going to see 3.5 spots as our mean number of spots, with a standard deviation of 1.7 spots. So I guess you can be labeling your mean, which we kind of did on the previous slide, and your standard deviation. Okay, let's take a look at the next problem. A box contains 5 balls. 2 are numbered 3, 1 is numbered 4, and 2 are numbered 5. The balls are mixed and one is selected at random. After a ball is selected, its number is recorded, then it is replaced. If the experiment is repeated many times, find the variance and standard deviation of the numbers on the balls. Well, we need to make a probability distribution so we can do some calculations. It says that the numbers on the balls are 3, 4, and 5. 2 of them are numbered 3, so 2 out of the 5. 1 of them is numbered 4, so 1 out of the 5. And 2 of them are numbered 5, so 2 out of the 5. Okay, now that we have our probability distribution, we can start finding the variance and the standard deviation. However, the formula for variance and standard deviation requires the mean. So we need to do a quick calculation over here. Remember, to find the mean, you're going to take the x value, you're going to multiply by the probability 2/5. Then you're going to take the x value 4 and multiply by 1/5. Plus, you're going to take 5 and multiply by 2/5. If I do this, I get 20/5 or 4. All right, so our mean is 4. That means the average number that will show when I pull a ball out of the box is 4. All right, so now we can find the standard deviation and the variance. So variance is first. So we're going to start our parenthesis, take our x value 3, square it, and multiply by its corresponding probability, which is 2/5. Plus, take your next x value 4, square it, and multiply it by its corresponding probability 1/5. Plus, your next x value 5, square it, multiply by its corresponding probability 2/5. Close your parenthesis, minus, then take your mean 4 and square it. So if you do this on your calculator and round it to one decimal place, you're going to get 0.8. So there's your variance. And then your standard deviation is the square root of whatever you have on your calculator. And so if you round that to one decimal, you get 0.9. Okay, let's do one more of this type. A talk radio station has 4 telephone lines. If the host is unable to talk, like during a commercial, or is talking to another person, the other callers are placed on hold. When all lines are in use, others who are trying to call in get a busy signal. The probability that 0, 1, 2, 3, or 4 people will get through is shown in the probability distribution. Find the variance in standard deviation for the distribution, and then should the station have considered getting more phone lines installed? Okay, well, in order to find the variance in standard deviation, I first need to find the mean. So it looks like if I look at my probability distribution, 18% of the time, 0 people get through, 34% of the time, 1 person gets through, and so on. So I need to find the mean. So I'm going to take each of my x's and multiply by its p of x's. So I'm going to take 0 and multiply by 0.18 plus 1 times 0.34 plus 2 times 0.23 plus 3 times 0.21 plus 4 times 0.04. Okay, if I do this, I get a mean of 1.6. Remember, I rounded that value because I'm only allowed one decimal. Okay, now I can find the variance. So start my parenthesis. I take each x, square it, and multiply it by its probability. So 0 squared times 0.18 plus 1 squared times 0.34 plus 2 squared times 0.23 plus 3 squared times 0.21 plus 4 squared times 0.04, close that parenthesis, subtract your mean, 1.6 squared. If I do all this on my calculator, I get, and round to one decimal, I get 1.3. Then I can find, and so that's an answer. Then I can find the standard deviation by square rooting whatever's on my calculator. And if I round that to one decimal, I get 1.1 callers. There's my standard deviation. So then the question is now, should the station have considered getting more phone lines installed? Well, let's take a look and see what would be a normal window of callers. Remember, outliers are going to be outside of a certain range, and outliers are going to be somewhere between mu plus or minus 2 sigma. So if I take my mean, which is 1.6, and I plus or minus the standard 2 times the standard deviation, which is 1.1, I get, let's see, 1.6 minus 2.2, that's negative 0.6, but I don't really need the negatives because that doesn't make any sense. So then I do 1.6 plus 2.2, and that's 3.8 callers. So once I get to 3.8 callers, anything more than that is going to be considered an outlier. And it looks like only 4% of the time do people get a busy signal. So I would say no, very few callers would not be able to get through. Would not be able to get through. Okay, so we've talked about mean, we've talked about standard deviation, we've talked about variance. Now it's time to talk about expected value and gambling. So, expected value is used in various types of games of chance, also in insurance and in other areas such as decision theory. So basically, the idea behind expected value is that you can use probability to anticipate or to estimate what's going to happen, thereby trying to win money in some kind of a game or to cut down your insurance. So here is the expected value formula for a discrete random variable. Notice that the expected value formula is the exact same formula as the mean. And that's why, if you want to find the expected value of some kind of game, that's the same as finding the mean. So the formula for the expected value is the same as the formula for the theoretical mean. That's because the expected value is the theoretical mean of the probability distribution. Now, keep in mind that expected value problems almost always involve money, and so it's usually customary to round to the nearest cent, which is probably breaking the rounding rules that you've done previously. In gambling games, if your expected value of the game is zero, then the game is said to be fair. If the expected value of a game is positive, then the game is in favor of the player. That means that the player has a better than even chance of winning. And then if the expected value of the game is negative, then the game is said to be in favor of the house. That is, in the long run, that the players are going to lose money. So let's take a look at a situation and learn about expected value. So, for instance, we have 1,000 tickets that are sold at $1 each for a color television valued at $350. What is the expected value of the gain if you purchase one ticket? So, think about making a probability distribution and thinking about the amount of money that you would gain as your X value and the corresponding probabilities underneath it. Well, it says that you are selling a $1 ticket and you can either win the color TV or lose the color TV. It looks like there are 1,000 tickets that are sold and only one is going to win. So let's say that I win the color TV. Well, that means that I paid $1. It's valued at 350. So on average, I'm looking at a $349 gain. If I don't win the TV, therefore I lose it, I am down $1. Now there's only one out of 1,000 ways that I can win it, and there are 999 out of 1,000 ways that I can lose. So the expected value for the gain if I buy a ticket is the same as the mean. And so I'm going to take each of my X values and multiply by its corresponding probabilities and then add them all up. So 349 times 1 over 1,000 plus a negative 1 times 999 over 1,000. If I put this all into my calculator and hit enter, I get negative 65 cents. So if you ever have the chance to buy a $1 raffle ticket and they only sell 1,000 and the color TV that you're trying to win is worth $350, if you only buy a ticket, you're probably not going to win. You'll probably be down 65 cents. Okay, 6 balls numbered 1, 2, 3, 5, 8, and 13 are placed in a box. A ball is selected at random and its number is recorded and then it is replaced. Find the expected value of the numbers that will occur. Okay, so I have an X and I have a P of X. The numbers I can have are 1, 2, 3, 5, 8, and 13. The corresponding probabilities are 1/6 because there are 6 and each one is in there one time. So my expected value is the same as my mean. So I'm going to do 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 5 times 1/6 plus 8 times 1/6 plus 13 times 1/6. If I do this, I get an expected value of 5.3. So there's not actually a ball with 5.3 on it. However, if I do this many, many times and keep putting the ball back in and averaging, I would get 5.3. All right, kids, one application and then we are done. On March 28th of 1979, the nuclear generating facility at 3 Mile Island in Pennsylvania began discharging radiation into the atmosphere. People exposed to even low levels of radiation can experience health problems ranging from very mild to severe, even causing death. A local newspaper reported that 11 babies were born with kidney problems in the 3-county area surrounding the 3 Mile Island nuclear power plant. The expected value for that problem in infants in that area was 3. Answer the following questions. So, number 1, what does expected value mean? Expected value, by definition, is the mean of a discrete probability distribution. So, expected value is the mean in a discrete probability distribution. Probability distribution. Number 2, would you expect the exact value of 3 all of the time? The answer is no. 3 is what you would expect in the long run, but you will get different numbers besides 3 each time. So no, we would expect some variation. We would expect some variation. Number 3, if a news reporter stated that the number of cases of kidney problems in newborns was nearly 4 times as many as was usually expected, do you think pregnant mothers living in that area would be overly concerned? Well, yes, I think no matter what area you're living in, if the outcome was 4 times as much as usual, I think lots of people would be concerned. So, yes, I think most mothers would be concerned. And I think we can say everybody will probably, most mothers, but really we'll say everyone would be concerned. Okay, is it unlikely that 11 occurred by chance? Well, the expected number is 3. So 11 seems extremely big. So we'll say yes, the expected number of newborns is 3. So 11 seems unlikely. Seems too big to be likely to occur. Likely to occur. Are there any other statistics that could better inform the public? Well, instead of just telling us how many babies, maybe we want like a percentage or a rate or how many babies was that out of. So we would probably, let's see, a rate like the rate per 1,000 newborns. Like, is it 3 per 1,000 newborns? Or is it 3 per 100,000 newborns? A rate would be informative because it might be 3 babies, but is it 3 out of 4? Is it 3 out of 10? That completely changes things. So assume that 3 out of 2,500 babies were born with kidney problems in that 3-county area the year before the accident. Also assume that 11 out of 2,500 babies were born with kidney problems in that 3-county area the year after the accident. What is the real percentage increase in that abnormality? Okay, so here we go. Here's a rate. So if I take the after rate, which was 11 over 2,500, and subtract the before rate, which was 3 out of 2,500, we see that that's 8 out of 2,500. And when you look at it that way, 8 out of 2,500, kids, that's only 0.0032. That's an increase of 0.32%. So that would be the real percent increase. When you look at it like that, well, that didn't increase very much at all. Sure, 11 babies now have developed kidney problems instead of 3, but the overall increase is very, very small. So, do you think that pregnant mothers living in that area should be overly concerned after looking at the results in terms of rates? And the answer is no. This increase is not significant. This increase of 0.32% is not significant. It's less than 0.5%. I wouldn't be concerned. All right, kids, that's the end of section 5.2. If you have any questions, please let me know. And as always, keep calm and keep trucking.